Hello, here we are going to analyze the running time of quicksort algorithm. In the previous lecture, we already discussed about the quicksort algorithm, how the algorithm works and how the partitioning algorithm plays the important role in the quicksort algorithm. And we also discussed quicksort algorithm as a divide and conquer type approach. Now is the time to discuss the running time of Quicksort algorithm and check the best case, worst case and the average case running time of the algorithm. The running time of Quicksort depends on whether the partitioning is balanced or unbalanced, and this in turn depends on which elements are used for partitioning. If the partitioning is balanced, the algorithm runs asymptotically as first as order of n log n. And if the partitioning is unbalanced, however, it can run asymptotically as slow as order of n square. Next, we will investigate how Quicksort performs under the assumptions for balanced versus unbalanced partitioning. First of all, for partitioning n elements in Quicksort, we need order of n time, because in partitioning algorithm, both the counters I and j will traverse the whole subarray of size n that needs total c into n number of competitions, where c is a constant, and that ultimately comes down to order of n times. So that is clear that we need order of n times for partitioning n elements. Now in Quicksort, worst case occurs when the partitioning produces one region with n minus 1 elements, one with only one element. And if this unbalanced partitioning arises at every iteration, in that case Quicksort produces worst case running time, and in that case we can write running time of n elements is equal to running time of n minus 1 elements plus order of n. This order of n is required to partition the n element into n minus 1 element and 1 element, and since single element does not record any partitioning, that's why we remove the term t1. So this we can write summation of k is equal to 1 to n order of k. Ultimately it will produce n square. So the worst case running time of Quicksort is equal to order of n square. That thing also we may check using the recursion tree. Here initially we have n elements, and from that element after first iteration it will partition into one element and n minus 1 element. For that we required cn number of comparison. Then again from n minus 1 element it will again break to one element and n minus 2 element, and that also requires c n minus 1 number of comparison. In this way, if we break the recursion tree, ultimately it will break to single element, and for that this is, we can say, right skewed binary tree, and a right skewed binary tree have n number of level for n element. If we sum up all these comparison, it will produces order of n square. Thus, if the partitioning is maximally unbalanced at every recursive step of the algorithm, the running time of Quicksort will be order of n square. Next, we will check the best case running time of Quicksort algorithm. Now, if the partitioning procedure produces completely balanced partition, that is, the partitioning will be from n element to n by 2 element and another also n by 2 element, Quicksort in that case runs much faster. The recurrence equation is Tn is equal to 2 T n by 2 plus, we can write Cn. Cn is the number of comparison needed to partitioning the n elements. Now if we try to solve this recurrence relation, that will be 2 into t n by 4 plus 2c n by 2 plus cn, that is 2 to the power 4 t n by 2 to the power 4 plus cn, that ultimately comes down to the power k t n by 2 to the power k plus c k n, where we can assume for our simplicity n is in the order of 2. So 2 to the power k is equal to n, that is k is equal to log n. So we can replace this equation by using k is equal to log n. So Tn is equal to n T1 plus C log n into n. Now we assume that T1 is equal to 1. We can assume for a single element runtime is constant. So in that case, this is equal to C1 into n plus C log n into n. Here the dominating term is C log n. So we can write it C n log n. So that is, we can write the running time Tn is equal to order of n log n. So the best case running time of the quickshot algorithm is order of n log n. And we can see, now we can check the recursion tree where initially we have n elements, and from n elements the partitioning algorithm divides the n elements into two n by 2 partitions. For that we need cn number of comparison. Again from that it is a balanced partitioning. So at each step we need cn number of comparison, and at each step it is producing a completely balanced partition. So ultimately it will comes down to a single element node, and at each level we need cn number of comparison. And since it is a complete binary tree, level of the tree will be log n. So the complexity will be cn into log n, order will be n log n. Next we will discuss the average case running time. The average case running time of Quickshot is much closer to the best case than the worst case. Suppose for our example, partitioning algorithm always produces a 9 to 1 proportional split, which maybe at first looks quite unbalanced. Here the running time Tn is equal to T 9n by 10 plus T n by 10 plus Cn. This is the running time of the quickshot algorithm when the proportionality of the split at every level is 9 to 1. Here in the recursion tree, we can notice that at each level of the tree has cost Cn for partitioning the n number of elements, and this will continue until the first boundary condition reach at a depth log n base 10, and that is asymptotically same as log n, and then the level have cost at most Cn. The recursion terminate at the depth log n base 10 by 9, and that is also asymptotically same as log n. Thus, with a 9 to 1 proportional split at every level of recursion, which intuitively seems quite unbalanced, here also Quickshot runs in order of n log n times, as same as if the split were right down the middle. The reason is that any split of constant proportionality will ultimately have a recursion tree of depth order of log n, and where the cost at each level order of n. Thus the running time is therefore order of n log n, and this is true whenever the split has a constant proportionality. So the best case running time of quickshot algorithm is order of n log n, as well as average case running time also have time complexity order of n log n, and only at the worst case quickshot have the performance with the running time having order of n square. So thank you for the time being.